Last episode, we watched pure static learn to fall. We built a score field, a grid of arrows, each one pointing from noise toward data, and we let a single drifting particle follow those arrows step by step until it landed inside a real cluster. That worked. It was real math, not a magic trick. A Langevin path climbing the gradient of a learned density until chaos resolved into structure. But watch what happens if we just let that particle go, with nothing else attached. It drifts, it follows the arrows faithfully, and it lands somewhere, sometimes a face, sometimes a car, sometimes something we can't even name. The field doesn't care what it produces, only that it produces something plausible. That's the problem sitting at the center of every text-to-image model. An unconditional field guarantees realism, but it guarantees nothing about content. If 100 images live inside that field's basins of attraction, the particle will fall into one of them at random, and you have no say in which one. That's fine for a physics demo. It is completely useless for a product where a user types a cat on a skateboard and expects, reliably, a cat on a skateboard, not a coffee mug, not a mountain, not a car. Somehow, 4 words of English need to reach into this purely geometric system and change where the particle falls. The fix is called conditioning, and the idea is almost embarrassingly simple once you see it. Give the network a second input. Instead of asking the UNet to predict what noise was added to this image, we ask it a slightly different question. What noise was added to this image, given that the image is supposed to match this description? In the notation of the field, our old unconditional predictor was epsilon of xt. The conditioned version is epsilon of xt, c, where c is some numerical encoding of your prompt, riding alongside the noisy latent at every single denoising step. So the real question this episode has to answer isn't, can we condition the model? Obviously we can, we just bolt on an extra input. The real question is geometric. What does that extra input actually do to the arrows? If conditioning is real, it shouldn't just be a label attached to the output. It should visibly bend the vector field itself, turn a single gravity well of anything realistic into a sharper, narrower gravity well of specifically this. Over the next 12 minutes, we are going to build that bend from the ground up. First, how words get into the network at all, then how they twist the arrows, and finally, the trick that makes that twist aggressive enough to actually work. Before a word can push a vector around, it has to stop being a word. A text encoder, the same family of model behind Clip, reads your prompt and converts every token into a list of numbers, an embedding. A point in a high-dimensional space where meaning has geometry. Cat lands near kitten and whiskers. Skateboard lands near wheels and ramp. This isn't metaphorical closeness, it's literal Euclidean closeness, measured in a space with hundreds of dimensions. Your 4-word prompt becomes a short sequence of these points, a small cloud of meaning, sitting there in numerical form, waiting to be used. Recall the UNet from episode 2, the funnel-shaped network that takes the noisy latent and predicts the noise inside it, squeezing the image down through narrowing layers and back up again. Deep inside that funnel, at multiple resolutions, sit special layers whose entire job is to let the image and the text talk to each other. These are cross-attention layers, and they are the doorway conditioning walks through. Nothing about the UNet's basic shape changes. The same convolutions, the same skip connections we saw before. We are simply inserting checkpoints where the image pauses and asks the prompt a question. Here is exactly what happens at one of those checkpoints. The image's own features at every spatial location generate a query vector. Think of it as the image asking, what should be here? Each word embedding from your prompt generates a key and a value vector. The network compares every query against every key with a dot product, runs the result through a softmax, and gets a set of attention weights, a distribution over how relevant is each word to this specific patch of the image. Those weights blend the values into a single vector that gets added back into the image's features. Every patch of the canvas literally votes on which words matter to it and pulls in a weighted mixture of their meaning. This is why magnet is the right picture and instruction is the wrong one. The text embeddings are not commands issued to the network. They are fixed points sitting in the UNet's feature space, and every location in the noisy image gets tugged toward whichever text magnets its own features resonate with. A patch that's already vaguely fur-shaped gets pulled hard toward the cat embedding. A patch that's vaguely disc-shaped and near the bottom of the frame gets pulled toward skateboard. Nothing is told what to draw. Every patch of static is simply nudged, dot product by dot product, toward the region of concept space its own noisy shape already half resembles. And this is the payoff for our vector field picture. Each cross-attention pass doesn't overwrite the UNet's noise prediction, it modifies it. The predicted arrow at every point in the field gets rotated, a little, toward the direction of the active text magnets. Across the whole denoising trajectory, hundreds of these small rotations compound. A field that once had one wide basin for any plausible photo now has its arrows visibly reshaped into a narrower channel that curves specifically toward cat-shaped, skateboard-shaped structure. The particle hasn't changed, the physics pulling on it has. Here's a strange fact buried in how these models are trained. During training, the text prompt is randomly deleted about 10% of the time and replaced with an empty string. At first, that sounds like sabotage. Why would you deliberately train the network to sometimes ignore the caption? The answer is that this single trick is the single biggest lever for prompt adherence in the entire pipeline, bigger than cross-attention itself. It's called Classifier-Free Guidance, and it works by making the network fluent in two different languages at once: what a cat looks like and what literally anything looks like. At every single step of generation, real deployed diffusion models do not run the UNet once. They run it twice, on the exact same noisy latent, at the exact same time step. The first pass includes your prompt embedding. Epsilon of XD, call this the conditional arrow, the direction the network would step if it's trying to honor a cat on a skateboard. The second pass feeds in an empty prompt. Epsilon of XD, empty set, the unconditional arrow, the direction the network steps towards some generic plausible image, with no opinion about cats or skateboards at all. Two predictions, same location, same instant, one aimed at your prompt, one aimed at everything. Now here is the actual trick, and it is nothing but vector arithmetic. Take the conditional arrow, subtract the unconditional arrow from it. What's left over, epsilon cond minus epsilon uncond, is a pure difference vector, the exact direction toward cat and skateboard and away from generic everything else. It isolates precisely what the prompt is contributing, with the network's generic prior subtracted clean out of it. This difference vector is the geometric fingerprint of your 4 words. Everything downstream in this chapter is just what we do with it. Classifier-free guidance is the formula epsilon guided equals epsilon uncond, plus a scale s, times that difference vector. In plain terms, start at the generic unconditional direction, then walk further, s times further, along exactly the direction your prompt was already pulling. If s equals 1, you just get the plain conditional prediction back, no extra push. If s is 7, or 12, or 20, the values real tools like Midjourney or Stable Diffusion expose as the CFG scale slider. You are extrapolating way past what the network actually predicted, aggressively overshooting in the prompt's favor. The slider every AI artist has dragged 1,000 times is nothing but this one scalar, s, multiplying one subtracted vector. Now, we can finally answer the video's opening question honestly. Turning the CFG slider up doesn't make the network think harder about your words. It takes the same 2 arrows, computes the same difference, and stretches it further before adding it back. Geometrically, this steepens the walls of the prompt's gravity well, narrower, deeper, harder for the particle to escape into a generic result. Turn it too far, and the extrapolation overshoots so aggressively that colors clip and textures fry. The well gets so steep it distorts the space around it. Turn it down, and the well flattens back toward the generic field, more creative freedom, less obedience to your exact words. Every turn it up for more prompt adherence tip you've ever read is this subtraction, this scalar, this single stretched arrow. Sit with the strange part for a second. To generate one image from one prompt, the model runs itself twice per step. Once imagining your cat, once imagining nothing in particular, purely so it can subtract one imagination from the other. It doesn't know what cat means the way you do. It knows the difference between a world with the word and a world without it, and it walks hard in that direction. That's not a black box being clever. That's linear algebra doing something that looks, from the outside, exactly like understanding. Everything we've built so far, the score field, the 2 UNet passes, the subtraction, the stretch, happens once per denoising step, and a real generation runs anywhere from 20 to 50 of those steps. If every step operated directly on a full resolution image, say 512 by 512 pixels across 3 color channels, that's over 780,000 numbers getting pushed through 2 forward passes of a large neural network, dozens of times for a single picture. Early pixel space diffusion models really did work this way, and they needed serious data center hardware to run at any reasonable speed. That is obviously not what's happening when your laptop generates an image in 8 seconds. The fix arrived with a paper that gave us the architecture behind stable diffusion, latent diffusion. Before any denoising happens, a separate, already trained network called a variational autoencoder compresses the image. Its encoder takes that 512 by 512 canvas and crushes it down, typically by a factor of 8 in each spatial dimension, into a tiny grid, something like 64 by 64, but with more channels per pixel to compensate. The total data shrinks by roughly a factor of 48. Crucially, this isn't lossy in the way that matters. The autoencoder is trained specifically, so this compressed representation still contains everything needed to reconstruct a sharp image later. Picture the difference directly. A giant, flat, two-dimensional grid of pixels, the visible image, gets folded down into a small three-dimensional block of numbers that looks like nothing recognizable to a human eye. There's no picture hiding in there if you tried to view its raw channels directly. It's an abstract, learned coordinate system, warped and compressed by the encoder specifically to be efficient for a neural network, not legible to us. This compressed block is the latent space. It is not a metaphor for the model's imagination. It is a literal, much smaller tensor that stands in for the image throughout the entire diffusion process. And here's the punchline. Every single thing from the last 2 chapters, the forward noising, the score field, the U-Net's noise prediction, the cross-attention magnets, the classifier-free guidance subtraction, all of it runs entirely inside this tiny compressed cube, never touching a full resolution pixel. The vector field we've spent 3 videos building doesn't live in pixel space at all. It lives in this cramped, 48 times smaller latent space, which is exactly why the whole loop, dozens of steps, 2 U-Net passes each, finishes in seconds instead of hours. This is the actual reason a text-to-image model fits inside a game GPU. Only once the denoising loop finishes, once the particle has been pulled by cross-attention and pushed by classifier-free guidance all the way to a clean point in that latent space, does a second half of the autoencoder, the decoder, take over. It upsamples the tiny final latent block back out to full pixel resolution, hallucinating the fine detail the encoder discarded, guided by everything the compressed representation still encodes. This is the very last step of the entire pipeline, and the only point where you, the human, ever actually see a pixel. Let's run the entire thing, start to finish, as one continuous motion. Your prompt is tokenized and embedded into text magnets. A patch of pure random noise is generated, but generated small, already living inside the compressed latent space, not in pixels. At every denoising step, the U-Net predicts 2 arrows across that latent field, one conditioned on your text magnets, one conditioned on nothing. Classifier-free guidance subtracts them, stretches the difference by your chosen scale, and produces one final, aggressively steered arrow. The particle steps along it, 20, 30, 50 times, the field bends a little more, the noise resolves a little further, until what's left is a clean point sitting in latent space, shaped like your words. Only then does the decoder unfold it back into the picture you actually see. 3 episodes ago, this all started with a single ink drop spreading in a glass of water, pure entropy, nothing controllable about it. And now, arrow by arrow, subtraction by subtraction, we've traced the entire path from that ink drop to a specific cat on a specific skateboard, appearing on command because you typed 4 words into a box. There was never a hidden mind in there interpreting your request. There was a gravity field, and your words warped it. Every diffusion model you'll ever use, Midjourney, Stable Diffusion, whatever comes next, is running exactly this. An observable, buildable, fully explainable machine. Not magic, just vectors, finally, learning to listen.